Well, hi again, and welcome to 7-2, Estimating a Population Mean. Okay, so key concept. The main goal of this section is to present methods for using a sample mean. So we're going to be using a sample mean to make an inference about the value of the corresponding population mean. So basically, they're going to give me a sample mean, and I'm going to do something, and I'm going to say, and what I'm going to do is talk about the entire population mean just from our sample mean. Okay. So in this section, there are three main concepts. The point estimate. So a point estimate is always going to be the sample mean. Okay. It's the best point estimate that we have. And if that's all, if they ask us for a point estimate, that's what we give. Then we also are going to give a confidence interval. So we're going to use sample data to construct and interpret a confidence interval estimate of the true value of the population mean. Basically, what that means is that we're going to say we have here mu, and it is between a lower bound, and we'll learn how to find that out, and an upper bound. Okay. And then we're also going to find sample size. So meaning that given some information, we want to find how many people we have to sample to get an estimate of the population mean. Okay. So some notation, most of it's not new, but so here we have it. Estimate a population mean with unknown sigma. This is really important right here. The sigma is not known. And sigma represents the standard deviation for the population. So we have our notation. We know that mu is the population mean, n is the number of sample, here, this is mu, n is the number of sample values, and x bar is the sample mean. Now we're going to add on to that our margin of error, which is E, and our sample standard deviation. This is not our population standard deviation. This is our sample standard deviation. And what are the requirements? Basically, the requirements are the same requirements that we had for the central limit theorem. The sample is a simple random sample, and either or both of these conditions are satisfied. The population is normally distributed, or, well, it could be both. Then n, which is the number of sample values, is greater than 30. Okay, so we're going to see a lot of formulas here. I'm not actually expecting you to use them. I'm just showing them to you. I'm going to show you how to use StatGrunch, so don't worry. But I am going to explain what we have here. So E is the margin of error, okay? And notice we're using, instead of Z sub alpha over 2, we're using T sub alpha over 2. And we're going to talk about what that means shortly. And S is the sample standard deviation, and N is the sample size. And then this right here, use DF equals N minus 1. DF is, well, it's actually down here. It's the degrees of freedom. And so I guess if you give me a minute, I'll talk about it at the end of this page. Then we have a confidence interval. It's a range of numbers used to estimate a population parameter. Okay, so based on, so we're going to give, like, just like I said in the last slide, we want to estimate our population parameter mu, because our population mean, and but we don't know what it is. So we're going to give a range. We're going to give a bottom, like a upper level and a lower level. And we know, and we're going to say that with some confidence, so this is our confidence level. Here we're talking about a 95% confidence level. With some confidence level, we're going to say we have a 95% confidence that our population mean is somewhere in this interval. That's basically what that's going to mean. Okay. So let's see. Alpha, which is the same alpha that I'm seeing right here, is the complement of the confidence level. The complement means 1 minus. So if we're looking for a 95% confidence interval, that means that alpha, the confidence level, is going to be 0.05. Okay. And then what we're going to do is we're going to say, okay, so we have this normal curve. And if I want a 95% confidence level, a 95% confidence interval, the confidence level is going to be 1 minus, oops, that was not what I meant to do. So it's going to be 1 minus 0.95, which is equal to 0.05. There's my alpha. But remember, we're actually looking for, we're going to split that in half. And why are we going to split that in half? Because we have this symmetry. So we want this part of the graph and this part of the graph to be 0.025. Because if you add those two together, you're going to end up with 0.05. And in the middle, so if those two ends add up to 0.05, then what's in the middle? I'll just do this. What's in here is our range. Okay, and that's what we're trying to find. So one thing we're going to do is we're going to find the critical value. Remember, what's the critical value? The critical value is this number right here, right? So the critical value is the critical t-value separating an area of alpha over 2, which in the case of 0.95 is, so alpha is 0.05, so alpha over 2 is 0.025 in the right tail of the student distribution. So that means this is the right tail. And basically what that does is it makes sure that we get a positive value. We could use the left tail, but we have to take the absolute value because we want t, that t of alpha over 2 is always going to be positive. Now let's talk about degrees of freedom. So the degrees of freedom is always going to be the sample size minus 1. And what does that mean? So let's say we have, we know that we want to find a mean, okay? So let's say we want the mean to be 5. And we have some numbers. Let's say we have 2 and 3 and 5. And we have some number, oops. We have some number, let's see, I'll just draw a circle here. It's not a 0, so I won't draw a circle. I have some number that I don't know. Remember, I don't know this number. But if I have that degree of freedom, this is divided by, well, if we want to find the mean, we add up all the values and we divide by the number of values. So 1, 2, 3, 4. Okay. And if I don't have this value, which is why I need at least one, so I need the degrees of freedom to be at least one less than the total sample, because I can now solve this. I can multiply both sides by 4 and get 20 equals 2 plus 3 plus 5 plus blank. And this is 10. 2 plus 3 plus 5 is 10. So we have 20 is equal to 10 plus some number. And now we know that that number is equal to 10. So I couldn't state my mean if I didn't have a degree of freedom, because it would automatically be given to me. If I knew every number, that's all I could do is calculate the mean. So hopefully that makes sense. Okay, so estimating a population mean with an unknown sigma. Unknown sigma. Okay, and how we're going to round it. And of course, you're going to round it to what Pearson tells you to round it to. But in general, if we have original data and we're using data instead of data summary, then we round the confidence interval limit to one more decimal place than is used in the original. One more decimal place than the original set of data. If we're given summary stats, then we just use the value that we were given. So when using the summary stats N, X, and S, round the confidence interval limits to the same number of decimal places used for the sample mean. So we're going to have a sample mean somewhere, X bar, and whatever that is, that's what we're rounding to. Okay, X bar. Now, there's some key points about this student t-distribution. First of all, it's really just called that. There's a story in the book about it. A guy worked in a brewery and he needed to be able to find out statistical information, but he didn't have enough data. He didn't have enough. It wasn't a big business, it was a small business. So he came up with this T distribution. Mostly we call it the T distribution, and it says that right here. So a student T distribution is commonly referred to as a T distribution. And you'll see that we're using the T distribution in StatCrunch. And so if a population has a normal distribution, then the distribution of T is equal to the sample mean minus the population mean. And notice we don't have the population. We don't have sigma for the population, so we use S for the sample divided by the square root of N. Again, we're not going to use these, right? But this is how things are calculated. All right, so degrees of freedom. Finding a critical value, T of alpha over 2, requires a value for the degrees of freedom. So in general, the number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data. Just like the example I just gave you, I could just vary one number and that's enough to make my values work, right? For the method of this section, the number of degrees of freedom is the sample size minus 1. So we are going to just use sample size minus 1. Okay. So key points about the student t-distribution. So if we want to find the critical value, T sub alpha over 2, we can either use technology, which is what we're going to use, or we could use a table. And I do have a table here, but I'm not sure if this is a T distribution table. Yes, it is. Okay, so this is what a T distribution table would look like. So if I had alpha over 2 is equal to 0.25, here, let me make this a little bigger. I think I can make it bigger. Hold on. Zoom. Sure. Nope. I guess I can. So I'm not sure if you can see it. Let me see what I can do here. That's okay. So down here, notice we have our confidence levels. So if you wanted 95%, these are the most standard, 90, 95, and 99. That's most standard. But here's our 95. And if we go up here, notice if we want just one tail, which is the right tail, we would use 0.025. Okay. And then we would look at our degrees of freedom. And this is our degrees of freedom over on this side. So let's say we had 20 values in our sample size, then our degrees of freedom are going to be 19. So we would look here and we would find 2.093 would be our 95% confidence level with 19 degrees of freedom. Okay, so let's go back to where we were, but I wanted to show you a table. Okay, so here we saw the table. And technology can be used with any number of degrees of freedom. The table, as you saw, only had certain degrees of freedom. So notice, do I have something that's 50? No, I have 40, 60. So with technology, we have everything. Let's see. So the student T distribution is different for different sample sizes. See the figure over here. So basically, the green is my standard normal distribution. And if you notice, the blue line is my T distribution where N is 3. That's kind of small. Number of samples is 3. Now, look how much closer it gets to the green when I make N equal 12. So that's why we've been, when it's 31 or more, that's why we've been able to say, okay, well, then we can just use our standard normal distribution or our Z tables, right? The student T distribution has the same general shape and symmetry as the standard normal distribution, but it has greater variability. That means we need more, we really need to make the intervals bigger to make sure we get our information in that interval. That is expected with small samples. Okay, so we'll see a little bit of this as well. Key points. The student T distribution has the same general symmetric bell shape as the standard normal distribution. We just saw that, but has more variability with wider distributions as we expect with small samples. So basically what that's saying is, because we don't really know a lot, we definitely don't know the standard deviation for the population, we're kind of estimating. So we're gonna make a little wider range for our mean to fall into. I'm not sure if that's clear. I think some of this is going to be more clear as we start doing problems. The student T distribution has a mean of T equals 0. Well, just like our standard normal had a z equals 0. That was the middle, right? The standard deviation of the student t distribution varies with the sample size, but is greater than 1. Because remember, with a normal standard distribution, our mean is 0 and our standard deviation is 1. So that's something that's a little different, okay? And as the sample size n gets larger, the student t distribution gets closer to the standard normal distribution. So the bigger the size of our sample, the more it's going to represent a standard normal distribution. Okay, so now this is a procedure that if you were doing it manually, you would have to go through. I'm going to tell you the parts that you have to go through for what we are doing, and we're going to use technology for some of it. So of course, we have to verify the two requirements are satisfied, that it's a simple random sample and the population is normally distributed, or n is greater than 30. So we have, it has to be a simple random sample, and then it could be either normally distributed, or n could be greater than 30, or it could be both of those. So here it says, as long as we have an unknown sigma, so that's our standard deviation, we don't know it, use n-1 degrees of freedom and use technology or a t distribution table. So with unknown sigma, we're going to use a t distribution table to find critical values. And I'm going to show you how to do that in StatCrunch. Evaluate the margin of error. We're not going to be doing that. That's really only for manual. I'll show you if we have a problem that needs that, I'll show you how to do it. Use the calculated margin of error and the value of the sample mean. Substitute those values in one of the formats for the confidence interval. Basically, what that says is, if we know, so this right here, I want you to understand it, even though we're not going to do it, but we will need it for some things. So here we have our normal, our bell curve, and here is our X bar. Right here, we're going to put our X bar, our sample mean, because that's all we have, right? And then we're going to calculate our error. And we're going to say, let me get another color. We're going to say this. So let's say this amount right here is E. So if I take X bar minus E, I'm going to be over here, aren't I? And if I take X bar plus E, I'm going to be over here. And again, this is E, right? My confidence interval is going to be, let's get a new color. My confidence interval is going to be from here to here. Okay? That's what this means. So that means our population mean, mu, we're saying is somewhere between X bar minus E and X bar plus E. And depending on what our confidence level is, that will depend on how wide that is or how small that is. Okay, so round the resulting confidence interval limits as follows. With an original set of data, round the confidence interval limits to one more decimal place than is used for the original data set. We already saw that. And when using summary statistics, round the interval to the same number of decimal places as used for the sample mean, which is right here. Whatever that value is, whatever the number of decimal places is. That's where we round to. Okay, so let's do an example here. It says find the critical value t of alpha over 2 corresponding to a 95% confidence level given that the sample has size n equals 15. Okay, well, actually, there's two ways we could do it. We could go to this table and we could, I guess we should remember what it says, 95% and size is 15. So 95%, size is 15. So our degrees of freedom is one less, which is 14. So there we have it. Let me erase the other one. Okay, so it is 2.145. Let's see what here we go. 2.145 from the table. Now let's find it on StatCrunch. So I am going to pause here for a second so I can get StatCrunch. All right, so we have our StatCrunch open. Let me see if I can make this a little. That looks a little better, I think. All right, so we're gonna go stat, calculators, and we're gonna go to T calculator. And notice here, it says degrees of freedom. And we have our sample size, I believe, was 15. And we can't see it, hold on. Sample size 15, so our degrees of freedom is 14. So I need to change this to 14. And I want a 95. So I want, remember, we want the t-score to always be bigger than, this would be t of alpha over 2, right? So this is 0.025 because we have 95%. So all I have to do is change this to greater than. And then I put in here 0.025. I hit compute, and there we have it. Same value, what it should be. So we get 2.145 from T calculator. Okay, and that's our critical value. If there's anything else here that we didn't say. I think I said everything. Here's a picture of what we just did. And you can see that there's 0.025 in this part and 0.025 in that part. And we're using the larger, we're using this, the right-hand side of our curve, which means that my t-score is always going to be positive. Very important to remember that. We did use the table. I showed you how to use the table already. So we're in good shape. And it says use column with 0.05 for the area in 2 tails, because we add them together, or the same column with 0.025 for the area in 1 tail. So this is what they mean. We used, here it says 95% confidence level. And up here at the top, it says 1 tail, 0.025, which is just the right side. But if I want to add both of those 2 sides, the right and the left side, it would be 0.05, or 1 minus 9. So really this is like saying 100% minus 95% is equal to 5%, which translates into 0.05, which is our alpha. Okay, I think we made it through that. Now we have a confidence interval. Said listed below are weights in hectograms or Hg of random, okay, so good. We have randomly selected girls at birth based on data from the National Center for Health Statistics. And we have summary stats. Okay, so what are we going to use here? Are we going to use a z-score or a t-score? Well, our n is 15. Well, that's small, but we only have sample information. We have x bar and we have s. We don't have mu and we don't have sigma. So we have to use our t-table, right? So what we're going to do is go back to StatCrunch. And for this one, I could put these values in and I could get the data off of the values, but I don't have to because they're giving me the summary data. So I can go here to t-stats, one sample with summary, and I put in my summary values. So X bar is 30.9, standard deviation 2.9, sample size 15. I click here, confidence interval, and I get, let's see, 95%, perfect. I can show my critical value if I want, and I hit compute. And this is what I get. This is my, so it's telling me a lot, right? There's my sample mean, my standard error, my degrees of freedom. There's my critical value that we already found for 15 people, 15, sample size of 15, right? And 95% confidence interval. And so I should have, and we have summary data, so we're going to use the same amount of decimals as the standard mean. So I'm going to say 29.3 is less than mu is less than 32.5. I'm 95% confident that my mu from the standard, from the entire population is somewhere between 29.3 and 32.5. Okay, that's the weight. So now we have some new information. In a test of the effectiveness of garlic for lowering cholesterol, 45 subjects were treated with garlic in a processed tablet form. Cholesterol levels were measured before and after the treatment. The changes before to after in their levels of LDL cholesterol have a mean of 3. So let's highlight the things that are important. The changes before and after in their levels of LDL cholesterol have a mean of 3.6 and a standard deviation of 15.2. Construct a 99% confidence interval estimate of the mean net change in LDL cholesterol after the garlic treatment. What does the confidence interval suggest about the effectiveness of garlic? Okay, one step at a time. So I look up here and I have to look to see if I have my requirements, right? So in a test of the effectiveness of garlic for lowering cholesterol, 45 subjects were treated with garlic in a processed tablet form. Okay, so far I have 45. So 45, n equals 45. That is greater than 30. So check. And I just need to know if it's random and then we're in good shape, right? Okay. Construct a 99% confidence interval estimate of the mean net change in LDL cholesterol after the garlic treatment. What does the confidence interval suggest about the effectiveness of garlic in reducing LDL? So, what do you think? Are we going to use a T-score? Or are we going to use a Z-score for this? And a test of the effectiveness of garlic for lowering cholesterol, 45 subjects. So 45 subjects, is that the population? No, that's N is 45, right? So let's write that down here. N equals 45. Okay, cholesterol levels were measured before and after the treatment. The changes before minus after. So basically, they're trying to find out if your cholesterol went down, it'll be a positive number, right? Because it'd be higher before and be lower after. And that value has a mean. And is that going to be a sample mean or a population mean? It's a sample mean. So that's going to be equal to 3.6. And the standard deviation, basically of the sample, that's small s, is equal to 15.2. And then we want to construct, so we have alpha is going to equal 1 minus 0.99, which equals 0.01, and alpha over 2 is equal to 0.005. Okay. And let's see what we got. So we go here to stat. Let me close my. We go here to stat, and we go to T stats, one sample with summary, and we put in our summary values. So we have mean is 3.6, standard deviation 15.2, sample size was 45, confidence level is 99, right? Yes, 99. So we're going to change this to a 9. Try. Okay. We can show the critical value, sure. And here's our values. Let's put them in and see what we get. To 2 decimal places, that is. And okay, so let's check our answer. Perfect. All right, erase this. Okay, what does the confidence interval suggest about the effectiveness of the treatment? Okay, so we have a confidence level of 99%. And we know our values. So let's read them. The confidence interval limits do not contain 0. Well, between a negative and a positive, that mu's got to get to 0. So that's not true. The confidence interval limits contain 0. Good. Suggesting that the garlic treatment and did affect the LDL cholesterol levels. All right, so far that's best. Confidence interval limits contain 0, suggesting that the garlic treatment did not. That is the actual correct answer. So we have um, we have this confidence interval, and it inside that interval there's a zero. So nothing may have changed at all. If we're saying that it's the before number minus the after number and that becomes zero, well then this didn't help at all, right? So let's see if that's correct. Perfect. Okay. Now it says a food safety guideline is that the mercury in fish should be below 1 part per million ppm. Listed below are the amounts of mercury parts per million found in tuna sushi sampled at different stores in a major city. Construct a 95% confidence interval estimate of the mean amount of mercury in the population. Does it appear there's too much mercury in tuna sushi? So what do we have to do? We have to check our requirements first. So let's see. Well, okay. So if it has more mercury than 1 part per million, it's not safe. Here's our data. So let's open StatCrunch with new data. And let's get rid of old StatCrunch. Oh, sorry. It's my, where's my mouse? Okay, here we go. Perfect. Okay. Okay, so we already went through this. And oh, that's right. Never mind. We didn't do this. We were doing problems, and I only did the first one. So I was just about to download the data into StatCrunch. Perfect. And now let's see what we're going to do. Well, okay, so let's look for our requirements. Well, we know what it has to be below 1 part per million. It really doesn't tell me anything, does it? How about if we use that graph, that QQ plot on the mercury, and I like putting a correlation statistic in there. It tells me how close I am to 1. And this looks good, right? I'm very close to 1. And they're very closely distributed around where they're supposed to be. So I'm in good shape. I can consider this normally distributed, okay? And what do I have for information? This is the amounts of mercury found in the tuna. And I need to construct a 95% confidence interval estimate of the mean amount of mercury. Okay, so let's go to, so are we going to need a T or a Z? Well, we're going to need a T-score because we don't have 30 numbers. We did say it's normally distributed, but we don't have very much data. So we're going to use our T calculator. 1 sample with data. There's my data. confidence interval of 95%. Ah, and now look, when I'm only looking for one value, I can actually plot this. And I can see at the same time, is it actually normally distributed? Which I already showed you it was, but there it is. So everything goes well. What is the confidence interval estimate of the population of mu? I want my lower limit to 3 decimal places. So that stays like that. And my upper limit, oh, and that is going to round up to 9. And perfect. Now it says, does it appear that there's too much mercury in tuna sushi? Well, if we look at our data, that's a pretty big range of data, right? And we can already see here, this one, 1.25 is already over, which means it's dangerous. 0.10 is below here. It's not, it's an outlier as well. So, no, because it is not possible that the mean is greater than 1 part per million. Well, there's the mean. That's not true. Yes, because it is possible that the mean is greater than 1 per million, 1 part per million. Also, at least one of the sample values exceeds 1 part per million. So at least some of the fish have too much mercury. So far, that's the best one. No, because it is possible that the mean is not greater than 1 part per million. Oh. It is possible that the mean is not greater than 1 part per million. Okay. Also, at least one of the sample data values is less than 1 part per million. So at least some of the fish are safe. So I only have one that's above this 1.25. And then the last thing says yes. So the question is, does it appear that there is too much mercury in tuna sushi? Yes, because it is possible that the mean is not greater than 1 part per million. And also, at least one of the sample values exceeds 1 part per million. So at least some of the fish have too much mercury. All right, let's see the difference between those two. Okay, so the mean is, well, the mean, it is possible that the mean is greater than 1. It can go all the way up to, this is our upper limit. So it's got to be that one. Perfect. And then, let's see, the last question I have here is about, let's see, hold on. Just having to plug my computer in. Better. Okay, refer to the accompanying data set and construct a 90% confidence interval estimate of the mean pulse rate of adult females. Then do the same for adult males, compare the results. Basically, We have males and females. I'm going to open StatCrunch with the data that they're giving me. So I'm going to open it again. And okay, I can close this. Construct a 90% confidence interval of the mean pulse rate for adult females. Again, let's look and see if we have the requirements for a T or a Z score. So we have well, we can do, let's do, so we'll do our females first. Let's go graph the QQ plot for females and see if it's normally distributed. Looks beautiful. Okay, we can even put our correlation coefficient. And look, it almost won, perfect. Okay, and so I now know it's normally distributed, and I have actually quite a bit of values. I have 40 values, so I'm in pretty good shape. I say Z score. What do you guys say? Let's see. So we'll go to stat. No, wait, it has to be a T score because we don't know the standard deviation. That's really what we want to look for. Do we know the standard deviation? And we do not. So we have to do a T-stat. One sample with data. And we're using females. 90%, so that's 0.9 or 0.90. And sure, we can put that plot, hit compute, and we're given that the lower limit to 1 decimal place, 72.8. And our upper limit, 79.8. Let's see what we got. Perfect. Construct a 90% confidence interval of the mean weight for adult males. Similar, just we're going to go up here, options, edit. And instead of females, we're going to pick males. Other than that, everything is the same. So compute. And let's look if it's normal. Yeah, it's very normally distributed, so we're in good shape. And so we have our lower limit to 1 decimal place. Actually, it's going to be 64. And our upper is 70.68. Oh, what did I do? Am I in the wrong calculator? I'm in a T. Okay, 90%. Let's go look at it again. So we have males, yes. 90%, yes. Oh, I didn't round this to 1 decimal place. 7. There we go. And I think that we're going to wait on 4. Oh, wait, sorry. I still have another question. Compare the results. The confidence intervals do not overlap. Well, let's see. This goes from 64 to 70.17. They do not overlap. So that's true. So it appears that adult females have a higher mean pulse rate than adult males. Here's females, here's males. That's true. The confidence intervals overlap? No. The confidence intervals, they do not overlap. So it appears that there is no difference in mean pulse rates between adult females and adult males. Well, it's not true. Since they don't overlap, there's quite a bit of difference. So I'm gonna stick with A. All right, very good. And I do believe that that is going to be our last question. Yes, we're going to do that in a little bit. So that's the end of this portion of the lecture. Thank you for watching.